Welcome to EDU World Space.
At the turn of the 1900s, two scientists, Rayleigh and Jeans, came up with a formula for the spectral irradiance of a black body. And this is known as the Rayleigh-Jeans law. They used what was known about electromagnetic radiation and developed a formula that did not match reality. So they determined the Rayleigh-Jeans function as the irradiance is 2 times the speed of light times the Boltzmann's constant times the temperature in Kelvin divided by the wavelength to the 4th power. So this applied to a black body spectrum as a function of wavelength in particular. And there's a problem with this. According to this theory, according to this formula, the spectral irradiance would explode at very short wavelengths, meaning that the black body should produce all of its energy at such a short wavelength it would be invisible. In other words, the black body would explode with an infinity of very short wavelengths. This is not what happens. So this is known as the ultraviolet catastrophe. Nobody exploded, but the formula was a catastrophe. A revision came along with the Planck function for the spectral irradiance. Now, what Planck did is he modeled a black body as a series of harmonic oscillators emitting photons, little bundles of energy, according to the oscillations, the distribution of oscillations. So it was inherently a quantum formula as well as a statistical mechanics formulation. Now I have off to the left plotted both functions. The Rayleigh-Jeans is the orange. The blue is the Planck function. We can see that at long wavelengths they agree, and I should point out that this is the functions plotted for a temperature of about 5,800 degrees Kelvin, which is our sun approximately. So do notice that the Planck function has a maximum around 500 nanometers, a yellow color like our sun. The two agree at long wavelengths. They differ by about a factor of 2 when you start to get below about 2,000 nanometers. So if we look at the data table, we see that, yes, they get off by about a factor of 2 between 1950 and 2,000 nanometers. So how does this agree with why does it agree with the Rayleigh-Jeans law? They agree at long wavelengths. And let's see why. So we're going to look at the argument of the exponential in the Planck function. But we're going to make the assumption that hc over kBt, which has the units of meters, that is much smaller than the lambda. And the exponential then looks like e to the x with a very small x. which we can approximate with the Taylor series as 1 plus x. In that case, the denominator in the Planck function is going to basically look like e to the hc over lambda kbt is going to be approximate, and we'll subtract the 1 too from there, just make that go away. That whole denominator is basically hc over lambda kbt. We can put that back into the b of lambda, and we get approximately 2 hc squared lambda to the minus 5 hc, and then get the numerator into the denominator into the numerator. Yeah, that's better. So some things will cancel. Let's see what else. Yes, 1 power of lambda goes up by 1. And so notice what we get. We get exactly the Rayleigh-Jeans function. So yes, there's reason why they agree at the long wavelengths. And it's probably because quantum physics usually does work in some regime, and it also agrees with classical in another regime.